This is a model of a clock which 200 years ago helped to revolutionize accurate navigation at sea. And this model is based on an earlier design by Galileo, the first known clock mechanism to use a pendulum. All these designs, springs or pendulums, fast or slow, have a similar pattern of movement. For example, how does a pendulum move? Is it like this? Well, the time taken for each cycle of motion is correct, but the pattern of movement is definitely wrong. The spot here is simply moving to and fro at a steady speed. So if a steady speed is wrong, what's the correct pattern of motion? What about this? Here, the speed of the spot is changing all the time. And this does match the pendulum's motion. But to make it quite clear what pattern of motion it is, let's see it happen more slowly. Notice how the spot slows down, speeds up, slows down. The speed is changing all the time. Now compare with the pattern of movement we had at first, the one that didn't match the pendulum. Concentrate on the lower trace. Notice how the speed stays the same all the way across. Now keep looking at the lower trace, but notice also how the other one overtakes, lags behind, overtakes. This pattern of motion with changing speed is called simple harmonic motion. It's a pattern we see time and time again when things oscillate. Even though the movement here is a rotation, the pattern of rotation follows the same routine. Speed up, slow down, speed up again. A bee's buzz sounds as it does because its wings oscillate more than 200 times a second. The sound is the natural sound, the picture is slow motion. Sounds are made by things that vibrate. Seen in slow motion, a cymbal has a very curious form of vibration. Here's a very simple example. A man with a plank. The plank oscillates just a little. But see what happens when the rhythm increases. The steps now match the frequency of the plank's own natural oscillation. Another example. While the engine is revving, the mirror is fairly free from vibration. But as the motor speed drops, it matches the resonance frequency of the mirror and the arm that it's mounted on. The result, a much stronger vibration. This may also be familiar. The front panel of this spin dryer has a natural resonance at about 40 hertz. That's 40 vibrations every second. There's a powerful response as the vibration from the motor reaches that critical frequency. All machines have parts that resonate, and it's very important to see that they're strong enough. Mounted on this vibration tester is electronic equipment designed for service on an aircraft. And now see it in slow motion. It's almost as though it's made of rubber. As the frequency of vibration is altered, resonances of individual sections of the assembly can be singled out. Even a light bulb may have to withstand vibration. The critical component here is the filament. This has its own individual frequency of resonance. Before this bridge was open to traffic, there had been some signs that it wasn't rigid enough. And this is what happened one day in November 1940. The driving force for this incredible event was wind. But how can wind give rise to oscillations? Well, here's a clue. An electric fan and a flat beam held in place by springs. As the fan starts, the beam just jostles around. But after some time has elapsed, a large and regular oscillation sets in. But this demonstration alone doesn't explain how an oscillation can be caused by a steady flow of air. But it does become clear if we use a wind tunnel, with the airflow marked with streamers of smoke. What we can see now is that the turbulence causes a regular up and down movement of the airflow. You can almost feel the beam being pulled up and down with it. And it comes at just the rate which matches the beam's natural oscillation. With each oscillation, energy is absorbed, so eventually the movement becomes quite large. There was no loss of life, but the collapse of this bridge over Tacoma Narrows in the USA taught engineers lessons that they've never forgotten. Some say that the effect of vibration on the human body can do you positive good. Certainly it can produce pleasant sensations. But whatever it does or doesn't do, seen in slow motion, the effect is pretty amazing. To take this line of investigation further, here's Michael Rodd.
One of the most intriguing things about vibration is the effect that it has on us. The human body isn't rigid, it's more like a piece of rubber. And when it's vibrated, this rubberiness can make some quite curious things happen. I'm at the University of Southampton, where they have machines like this seat on which I'm sitting. Now it is vibrating my whole body, both up and down and side to side at the same time. And the frequency of vibration is controlled by turning this knob. Now one thing that vibration can do is affect the normal operation of our lungs and our larynx, which together enable us to speak. As the frequency of vibration increases, my voice becomes more and more affected. Eventually, it becomes very difficult for me to speak normally at all. Now, I am trying to speak to you perfectly normally. I'm not altering my voice consciously in any way. The effect that you are hearing now is something over which I have absolutely no control. Until that is, I switch off. The whole human body is made up of many different parts, all connected by pieces of rubbery tissue. And each of these different parts has an individual response to vibration. Let me show you what I mean. And because we've already discovered that it's very difficult to talk while being vibrated, I'll take the easy way out. We'll add the commentary later. Right.
The first clear body resonance comes at about 5 hertz, 5 vibrations each second. We're seeing the film slowed down, of course. At higher frequencies, other parts of the body are affected. In point of fact, we each have our own particular set of body resonances. The results are never precisely the same for any two people.
Interesting though those vibration effects are, what is really important is that they can have serious practical consequences. One example. Do you remember the resonance that affected the region round my eye? What you certainly couldn't see was that my eyeball itself was also moving. Just a tiny vibration, but serious enough to have a bad effect on my vision. Now, it's not too hard to realize there are situations where blurred vision caused by vibration could be exceedingly dangerous.
Not long ago, there were a number of unexplained helicopter accidents. Many involved collisions with electricity power lines. It's now realized that if the pylons are obscured by trees perhaps, the power lines themselves might be rendered quite invisible by a resonance of the pilot's eyeballs due to vibration. We'll show a simulation of a pilot's vision, somewhat exaggerated, to illustrate the point. It will show just how dangerous things could be, particularly in conditions of fading light. Obviously, in this case, the pylons are visible, but in other circumstances, it seems pilots have been less fortunate. The crew of this helicopter survived. Others haven't. In aircraft and other machines, careful tests and good design are essential to minimize the dangers. For example, maybe the seats can be improved to absorb vibration more effectively. And of course, the machines themselves must withstand vibration too.